logic being installed on a web server and the data store being hosted on a separate server. Now, with systems like this, you don't have to look very far.
Hi everyone, my name is Stefan Roman and welcome to my course AWS DynamoDB Fundamentals, a course that introduces you to critical knowledge for building serverless applications. I am a DevOps engineer here at Piano Software based in Slovakia. My day-to-day tasks range from ensuring continuous delivery of software by automating various AWS services to architecting elastic and robust infrastructure on AWS, including managing dozens of DynamoDB tables. DynamoDB is a fully managed NoSQL database that can provide you with stable and elastic database. It provides significant cost savings due to its serverless nature, as well as zero downtime auto-scaling and backup features. Therefore, knowing such service is really beneficial for architecting and development of your own applications or even offloading operational costs bound with traditional databases. In this course, we are going to look at basic and advanced features of DynamoDB, from understanding basic concepts to auto-scaling features and calculating the required capacity to avoid unnecessary costs. We'll also look at best architectural practices of complex tables. Backing up tables and recovering lost table data. We will look at disaster recovery solutions offered by DynamoDB service, as well as solutions for data retention. Active and passive monitoring of DynamoDB tables, where we look at ways to produce alerts from various events and alarms that table might produce, as well as proactively monitor our tables. Interacting with DynamoDB items with Amazon Console, AWS command line tools, and Python. By the end of this course, you'll be able to architect reliable and cost-effective DynamoDB tables and interact with them according to the best practices. You'll also be able to monitor as well as provide appropriate backup solutions for your tables. You'll be able to integrate this knowledge for development of applications for personal use, as well as serious business ideas. Before taking this course, you should be familiar with JSON data type, bash scripting, as well as a little bit of Python programming. I hope you'll join me on this journey to learn DynamoDB with the AWS DynamoDB Fundamentals course at Pluralsight. Hey, this is Stefan Roman, and in this module we'll look at designing a simple DynamoDB table which will serve as a reliable database of employees in Globomantic's company. Before that, however, I'll describe what DynamoDB is, then we'll look at table components of DynamoDB and how they compare to components of tables used in relational databases. I'll also explain different types of primary keys and what role they play when working with DynamoDB items. We'll also go through how primary keys are used to partition and store data within Amazon infrastructure, and we'll also go through all data types that can be used in DynamoDB table. We'll finish off with a demo to show you how you can design a table with all this knowledge based on specific requirements given by Globomantic's developers. So what is DynamoDB? It is a fully managed NoSQL database service, all managed by AWS. This means that you don't have to worry about any administration of your database, which includes hardware provisioning, any type of configuration, replication and redundancy, software patching, or scaling. All of these are handled by AWS themselves. DynamoDB was created with elasticity in mind, which means that scaling of your database comes with no downtime seamlessly. We'll look at the scaling features of DynamoDB in the following module. DynamoDB also stores data across multiple availability zones to provide higher redundant data storage and data durability. We'll look at how DynamoDB stores data across partitions later on in this module. So let's dive in and look at simple DynamoDB components. DynamoDB has three basic components: item, attribute, and table. An item can be compared to a row in a relational database. An attribute can be compared to a column, and a DynamoDB table can be compared to a whole relational database. A good way to think about these components is that an item is a collection of attributes, and table is a collection of items. To further explain this concept, here is DynamoDB item in JSON format. In this case, this item looks like an employee record with employee name Bob. This item consists of identifiers of attributes also called keys. In this case, these are name, age, company, and position. And of course, attributes themselves, which are values of keys. In this case, Bob, 26, Globomantics, and DevOps. As mentioned previously, a table is a collection of items. Here is an example of a table consisting of multiple employees: Peter, Jane, Lucy, and Andy. So we talked about uniquely identifying an attribute in an item. But what about uniquely identifying an item within a table? Let's look at Bob employee record item again. You might have noticed in previous slides, I've set the color of name attribute key to a different color to others. This is because this particular attribute key uniquely identifies an item within a DynamoDB table. These special keys are called partition keys. Let me give you an example of what might happen to our employee record table in time with the partition key being the first name of an employee. We have Bob, who's our DevOps engineer already working at the company on the left. However, a new employee also named Bob is employed as an administrator on the right. This will result in partition key collision as two items are identified with the same partition key value. This way, we won't be able to update the table with the new employee item. How can we resolve this issue? We can add another special attribute alongside partition key called sort key. This ensures the uniqueness of an item is based on the combination of partition key as well as sort key, and not just partition key on its own. In this case, we choose Bob's age as the sort key. That way, we'll be able to have more employees named Bob in our table. In the world of DynamoDB, this concept is called a primary key of a table. There are two types of primary keys. Simple primary keys. These consist of only partition key described in the earlier version of our table, where Bob attribute uniquely identified an item. And composite primary keys consisting of both partition key and sort key described in the later version of our table, where Bob and Bob's age ensure the uniqueness of the item. So DynamoDB stores all data in hard drive partitions, which are all managed by AWS. However, with the use of primary key, you are able to somehow control where and how the data is stored. Let me explain by using a table with a simple primary key consisting of only partition key. At the moment, our table contains 3 items with partition key values Bob, Rebecca, and Emma. DynamoDB uses these values as input to an internal hash function. The output value of the hash function determines the partition in which the item will be stored. Let's look at how this works using composite primary keys. Let's say we'll use the same partition key being the name of the employee and sort key being employee's age. Partition key is Bob for all 3 items, however, sort key is different in all 3 cases. So what would happen? DynamoDB will calculate identical hashes from the partition key due to the value being Bob in all 3 cases. This in turn means that all 3 items will be stored on the same partition. Because we have a sort key set for each item, DynamoDB stores our items in ascending order by this sort key. Let's look at data types that can be stored within DynamoDB table. Scalar values, which store one value at a time. Document type values, which hold multiple values of different types. Set type, which hold multiple values of the same type. As you can see from the example, Bob is 26 years old and unemployed. So as per this table, item scalar values can be strings, integers, null, and boolean type. In this example, Bob is still unemployed, however hobbies attribute appears. This is a document data type holding the list of his favorite things. The list is composed from strings and an integer. In this example, Bob's kitchen tools are stored within the table item, with kitchen tools being a list document type. However, this list holds a map document type with the amount of spoons. We can also add the amount of forks or knives Bob has in his kitchen in the same map. In this example, Bob's favorite lottery numbers are stored in the table item. We used set data type with integer values. This is because we know the lottery numbers attribute will hold only set of numbers without strings nor maps. In this example, Bob's kids' names are stored within a string set, as we know that this attribute will not hold any other value other than a string. DynamoDB can also store binary data. In this example, we can see base64 encoded data stored as a scalar value named secret, or multiple base64 encoded values stored in a set called live secrets. As you can see, DynamoDB is flexible when it comes to data types. One very important aspect to keep in mind is that unlike in relational databases, a fixed schema is not required when creating and later when storing items within it. Only primary key attributes have to be present. Let me show you an example. Let's take an item from previous example where we looked at string sets. Let's say the primary key of this table consists of only partition key called name. We can therefore store this item from previous example. We can also store an item with a name attribute value set to Jane and no other attributes. And we can also store Peter's kitchen items in the same table as the previous two items. Globomantics developers have asked us to build a table that will store employee data. The prerequisites are that the table has to have employee's first name as the partition key and their age as the sort key. In this case, we'll name the table Simple Employee Table. Its partition key attribute name will be set to name with a capital N, and sort key attribute name will be set to age with a capital A. So here we are in the Amazon console. Our developers didn't really specify any kind of Amazon region, so we can just stay in the region that we are. Let's search for DynamoDB. Let's click on Create Table. Let's call this table Simple Employee Table, as we decided. Let's call the partition key name with a capital N. Let's add a sort key and call it age with a capital A. In this case, we can also change the data type from string to a number, since we'll always use an integer for age. And let's just keep all default settings and click create and wait until the table provisions. Now that we have our table provisioned, we can add some items. Click on items, then create item, and then click on text from the drop-down menu, because we will paste a JSON document and we will not need to fill every single key and attribute separately. Now, as you can see, there is our primary key already predefined with the name and age keys. We can remove them, as we will now paste our own JSON document. This document may look familiar, as we went through some of the data types in previous clips. For instance, you can see an integer set describing Bob's favorite lottery numbers, and also a map document type describing each of Bob's kids. You can download this JSON document from assets and play around with it. Now let's click on Save to store this item in our table. Now I would like to show you how flexible DynamoDB can be. Let's create a new item again and paste the same JSON document, but now we'll delete lottery numbers, kids, and add a few more keys which are not present in the previous item. So let's delete lottery numbers. Let's delete kids. Before saving, we'll also need to change the primary key. So let's change the name attribute to Alice and change her age to 22. Let's add plants key to specify how many plants Alice has at her home. And let's say she has 12 plants. Now let's click on Save. Now you can see how flexible DynamoDB can be without the predefined schema. All DynamoDB needs is a unique primary key, and all other keys and attributes can change. So in this module, we talked about what DynamoDB is, its elasticity and redundancy features. We also talked about basic table components where we compared DynamoDB components to relational databases. Here we also went through a simple DynamoDB item and described each item component. We spoke about what primary keys are and what primary key types there are. We also described disadvantages of a simple primary key and how to remedy that using composite primary key. In this module we also spoke about how DynamoDB uses primary keys to store data. We also spoke about various data types that can be stored within a DynamoDB table, and in the end we logged into the Amazon console and created a basic DynamoDB table and also stored two different items. Hey, this is Stefan Roman, and in this module we'll look at designing an elaborate DynamoDB table which will serve as a backend database for three applications, all requiring to query employee records of Globomantic's company in different ways. Before that, however, we'll go through two types of storage consistency. This will be required when I'll be talking about creating throughput capacity. We'll also learn about two types of autoscaling, which can adjust your table's capacity to its appropriate throughput. We'll then learn about two types of secretary index, where we'll also learn about using different ways to query data using the indices. We'll then go through creating a master-to-master replication, or otherwise called global table, where multiple tables in different regions are in sync with each other. We'll also learn about DynamoDB streams, which are essential to making global tables work. We'll also learn about designing an efficient partition and sort keys. And with this knowledge, we'll create an elaborate DynamoDB global table according to instructions from Globomantic's developers. In the previous module, we talked a little bit about storing items in our simple employee table. The question is, can we store and retrieve any amount of items at any time? The answer is no. There are certain limits to how many items we can query and store in a particular DynamoDB table. The limitations are separated into read and write limits, also known as write capacity units and read capacity units. All the abbreviations WCU and RCU. In AWS world, one write capacity unit consists of a single write operation of up to 1 kilobyte per second. The size of a write rounds up to 1 kilobyte even if the item being written is less than 1 kilobyte in size. For instance, if you write one item of 500 bytes every second, AWS would still treat it as 1 kilobyte write every second. Reads are a little bit more complex. As you can see, a single read capacity unit consists of 1 or 2 reads of 4 kilobytes per second. Now, as with writes, when a read is made below 4 kilobytes, AWS treats it as full 4 kilobyte read. What is different is that there are two types of reads, one being eventually consistent read, with which you can read an item of 4 kilobytes twice a second to consume a single read capacity unit. The second being strongly consistent read, with which you can read an item of up to 4 kilobytes once to consume a single read capacity unit. So why are strongly consistent reads more expensive? Let me explain this concept further. AWS attempts to replicate data across multiple availability zones in a region where tables are deployed to achieve data redundancy and data durability. Replication between different availability zones takes time, and when a read query is executed short time after an item is updated and DynamoDB decides to retrieve a requested item from availability zone where the item was not yet updated, the query might return all data. This is where storage consistency comes in. With eventually consistent reads, there is a risk that read queries executed too soon return all data. With strong consistency, data that's returned is always up to date and reflecting the updates from all previous write operations that were successful. Let's say that Emma writes an item to our table. Emma receives HTTP status code of 200, which means a successful write to one of the availability zones. After the initial write, DynamoDB will replicate the change to a partition in another availability zone. But what if Rebecca queries the table for updated item before the replication took place? She'll receive stale data back without Emma's change, hence the term eventual consistency. The data is eventually consistent across all DynamoDB partitions. What happens with strong consistency is that when Rebecca queries the table before replication took place, DynamoDB looks for most up-to-date item across all partitions and returns the most up-to-date data. This is also why it costs more to use strong consistency when querying data. As for use cases, eventually consistent reads can be used in applications that allow for a margin of error when querying table items or applications that do not query immediately after writing. Strongly consistent reads are for applications that do not allow for any margin of error, require up-to-date data, or have tendency to query items immediately after updating. DynamoDB provides autoscaling feature of read and write capacity units with no downtime. This is done by setting minimum and maximum read and write capacity units. A range is set so that DynamoDB can determine what you think the minimum capacity is when the table is being utilized the least, and what you expect during peak times by setting maximum capacity. However, how would an engineer calculate required capacity? Well, before such calculation, the engineer needs to know the approximate size of items written to and read from the table in kilobytes, the amount of such items being written to and read from the table every second, and what read consistency is required. Let's look at a simple example calculating read capacity units using eventual consistency. Application requires to read 10 items of around 1 kilobyte each per second using eventually consistent reads. First, we need to calculate how many read units per item are needed. We need to round up the size of the item being read to the nearest 4 kilobyte increment. In this case, 4 kilobytes. If we needed to read an item that's 5 kilobytes in size, we would round up to 8 kilobytes, but in this case it's only 4 kilobytes. We need to then divide this number by the size of one read unit to get how many read units are required for one item. In this case, 4 divided by 4 is one read unit per a 1 kilobyte item. We then take read units and multiply them by the amount of items required per second to get read capacity units. In this case, we need to read 10 items per second, each worth only one read unit. Therefore, we need 10 read capacity units. However, one small point. If you remember, I mentioned a single read capacity unit can consist of 1 or 2 read of 4 kilobytes. Well, because we are using eventually consistent reads, the result can be divided by 2, since eventually consistent reads consist of 2 reads per single 4 kilobyte item. Let's have a look at how to calculate strongly consistent reads. So in this case, application requires to read 4 items of around 14 kilobytes each per second using strongly consistent reads. Let's have a look at the calculation. So how many read units per item are needed in this case? We round up to the nearest 4 kilobyte increment, therefore 16 kilobytes is what we end up with. We need to divide 16 kilobytes by the size of one read unit, which is 4 kilobytes. We'll get that one item is worth 4 read units. We need to take the number of read units and multiply that by the number of the amount of items being read from the table. In this case, we get 40. Unlike with eventually consistent reads, which are much cheaper than strongly consistent reads, we need to divide by 1, which gives us 40 read capacity units. Let's have a look at how to calculate write capacity, which is much easier than calculating read capacity. So our application needs to write 10 items of around 7 kilobytes each per second to our table. Because a write is worth 1 kilobyte exactly, we only need to multiply the size of the item in kilobytes with the amount of items being written to the table every second. The result is 70 write capacity units in this case. In order to find the right minimum and maximum capacity, you need to know the average reads and writes per second as we've just discussed and predicted traffic patterns for some applications that tend to peak at certain times. Of course, we don't want to provision thousands and thousands of read and write capacity units well over the required capacity to compensate for such peaks, since it would cost us a lot of money. So what would happen in the event of miscalculation of capacity? What would happen when traffic to the table starts to go over provisioned capacity? Well, additional requests to the table over provisioned capacity would be throttled. What it means in practice is that additional requests to the table over provisioned capacity will fail. So what could be done in order to avoid request throttling when an application is extremely unpredictable? There is a solution for such application. It's called on-demand autoscaling. Here is a comparison of provisioned autoscaling, which we've just talked about, and on-demand autoscaling. Think of on-demand autoscaling as if you would set provisioned autoscaling from 1 to maximum throughput of DynamoDB can handle and let DynamoDB handle the rest. The difference is that provisioned autoscaling can be used for applications with predictable traffic patterns. On-demand autoscaling, on the other hand, can be used for applications with unpredictable traffic patterns. There is a difference in pricing model for each autoscaling method. You pay for provisioned capacity using provisioned autoscaling, but using on-demand autoscaling, you're paying for the amount of requests. Now this is a big difference worth a debate. With on-demand autoscaling, there is a risk of application producing a lot of requests to the table causing a big traffic spikes, but also causing price spikes out of your control. With provisioned autoscaling, you'll know exactly what the table is capable of consuming money-wise. But an unexpected traffic spike can cause request throttling and potentially unhappy customers. This is really up to what kind of application will be using your table and the level of knowledge about traffic patterns of your application. In order to understand secondary index, let's look at the following item. This is the item we described in previous examples. The item is stored within a table where primary key is composed of a partition key called name and sort key called age. If we want to query for this item, we have to use primary key values in order to retrieve this item. For example, our query might be get all items when name equals Bob and age is 26. What if we want to query using a different sort key, let's say position? In this case, the query could be get all items when name equals Bob and position is DevOps. What if we want to query using completely different primary key? Let's say our partition key could be company and sort key could be position. This is where secondary indices come in. They improve data accessibility of items in our table. There are two types of secondary indices: local secondary index and global secondary index. Let's talk about how they are different. Local secondary index has the same partition key but a different sort key. Let's look at an example. Let's say we want to query Bob based on age as well as query Bob based on company where he works at. This is where we could set up additional sort key for attribute company, otherwise called local secondary index. Global secondary index is a complete separate search index with its own partition and sort keys. Let's look at an example. We can query Bob based on his age, but we can also query items based on company name sorted by positions. This is what global secondary index would allow us to do. It's important to know that local secondary index is scoped to base table partitions due to partition key being the same. But global secondary index has completely unique primary key, therefore it spans across all partitions. Another difference is performance. Local secondary index shares its throughput with the base table. However, global secondary index has its own provisioned throughput. Another difference is how many of these you can have per table. 5 local secondary indices and 20 global secondary indices are maximum. When configuring a secondary index of any type, it's important to know about attribute projection. It's essentially how much data will be stored within your secondary index. You can choose one of the 3 attribute projection options. The first one is keys only. In this attribute projection, only partition and sort keys as well as key index values will be stored in the index, creating the smallest possible index. The second one is include. This includes keys only as well as explicitly specified non-key attributes. And all, which is the largest index, and this includes all source table attributes, creating essentially a copy of your entire table for your index to search. In the following demo, I'll quickly show you how you can create a table with a global as well as local secondary indices. Now that we are logged into the console, let's create our table. It doesn't really matter in which region is it in this case, so we can stay in Ohio. Let's create a table with the name of secondary index test. We can set the name as the partition key and age as the sort key. Let's also change the data type to integer for our sort key. Because the local secondary index can only be created when creating a table, we have to create a local secondary index now. But first, we have to uncheck Use Default Settings option for it to allow us create the index. Click Add Index. If you remember, local secondary index is just another sort key for our table. We can name our new sort key ID, since this will be the identification number for our employees. If you remember, in previous clips we learned that the primary key of local secondary indices must be the same as on the base table, so we have to specify name as the partition key again. As you can see, the checkbox for create as local secondary index is still grayed out. This is due to AWS thinking that we want to create this as a global secondary index, since we have not specified that we want to create another sort key with our index. If you remember, local secondary index is just another sort key for our table. We can name our new sort key ID, since this will be the identification number for our employees. We'll also change the data type to integer. As for the index name, we can choose to name it however we want. For this purpose, I'll name it local ID index. We also talked about projected attributes in previous clips. We can leave that to project all attributes. Now we have to check the box to create it as local secondary index. Now click Add Index and we'll leave all the other options default and click Create. We'll now wait until our table provisions. Here we go, our table is now provisioned. Now we can add global secondary index. Go to Indexes tab and click Create Index. You can see that this looks a little different. Because we are adding a global secondary index, we can now choose a different partition key. Let's choose ID as our partition key. And if you remember, we also have to change the data type of this attribute to number. And for the purposes of this demo, we won't be using any sort key for this index. We can also see that throughput of this index can also be set independently of the base table. But for the purposes of this demo, let's leave it as it is. Let's name this index Global ID Index and project all attributes again. And click Create Index. Now we'll wait until our index provisions. Now that both of our indices are provisioned, I can now query a couple of items to show you how we can access data using them. I've added a few items to the table already to help us out with the queries. Let's click on Items. We can use the base table for now to query our items. Let's say we want to query Bob items whose ages are more than 30. Here we have Bob who's 55. Let's try querying with the local secondary index. In this case, we can query Bob items whose IDs are less than 5. Here we have two items. With our secondary index, these items would be very difficult to recover using base table queries. Now let's try a global secondary index. We can now search for ID of 6. Here we have an item with name Peter. If we didn't know the name attribute of this item, it will be very difficult to recover without this index. DynamoDB offers functionality to replicate table items between multiple tables in different regions. For instance, when an application writes an item to a table in Sydney, it will get replicated to a table in Ireland. And when someone writes or updates an item in Ireland table, it will get replicated to Sydney. Such DynamoDB implementation is called a global table. What it essentially is a collection of tables with the same properties deployed in different regions. Its core functionality is to replicate item updates to all tables in a global table. This functionality is great for multi-region application where a user can connect to a table closest to them for minimal latency. There are few requirements before a single table can become a part of a global table. The same write capacity has to be provisioned on all tables within a global table. They all must have the same name. They must have the same primary key, simple or composite, it doesn't matter. And tables must be empty before assigning them to a global table. So it's the best if a global table is set up before storing any data within tables. Let's look at an example. We have tables located in Sydney and Ireland which are both parts of a global table. And we have Peter and Jane who will read from and write to our global table here. Peter updates an item within a table located in Ireland and the item update gets replicated in Sydney. Jane can then read the updated item from the Sydney table. Simple, right? However, what would happen if both Jane and Peter update the same item at the same time? AWS has implemented a feature where if simultaneous writes happen at the same time, DynamoDB determines the last writer. AWS calls it the last writer wins. Before we can start creating global tables, we have to enable DynamoDB streams. The purpose of these streams is to capture table activity which is required for tables to know what's happening with the other tables in a global table. You can use DynamoDB streams for other AWS services and applications also. The stream record contains information about data modification to a single item in the DynamoDB table. The stream records are kept for 24 hours. With the DynamoDB streams, you can specify information that is contained within a stream record. For instance, you can set the stream to produce records to keys only, which only includes the key attributes of the modified item. New image, which includes the entire item as it appears after it was modified. Old image, which includes the entire item as it appeared before it was modified. New and old images, which is the biggest record since it includes both new and old images of the item. In order for a global table to function correctly, it is required to enable stream of new and old images as the tables in a global table need to know exactly what the item looked like before and what it was modified to. But this is handled automatically when creating a global table. We'll now create a table with all default settings. We'll enable DynamoDB stream and create a replica table, and we'll input an item into our simple table and observe replication to our secondary table. It doesn't matter in which region we create our initial table in this case, so we can stay in Ohio for now. Let's create a table and call it global table. We can name our partition key name. In this case, we won't use sort key. We'll also use all default settings here. Let's create this table. Now we'll wait until our table provisions. Let's go to Global Tables tab. First we have to enable DynamoDB streams in order for the replication to work. As you can see, only one option for level of data included in stream records is available. As we talked about, global tables require all the new image information in any stream record to function correctly. Click Enable to enable the stream. Now click Add Region and choose a region of your preference. In this case, I'll choose Frankfurt. Click Continue and wait until a new table provisions in the region of your preference. The message says that the new replica has been successfully created. So now we can go ahead and store our item and observe replication. Let's close this. Let's click on Items tab and click Create Items. Because we'll copy and paste JSON document, switch to text editor. We'll paste our item and click Save. Now go to our table in Frankfurt region to see whether the item got replicated. Click on Items. Now we can see that the item appears here with few more attributes. The attributes describe from what region the update originated from, when it was updated, and whether the item is being deleted by replication, in this case is false. Let's go through some of the smaller DynamoDB features. First is encryption. Table encryption is enabled by default at rest, which means that data stored on disks is automatically encrypted so that a person cannot just steal a hard drive and see your data. And also data is encrypted in transit by using SSL certificates when updating, adding or deleting table items, so that a person who might be listening to traffic between you and DynamoDB table is not able to read anything. Encryption also applies to DynamoDB streams, as well as global and local secondary indices. Another feature which can come in very useful to certain types of tables and items is time to live. With time to live, you can set an item expiration by adding a TTL attribute to an item with the value of expiration time in epoch format. Let me show you what I mean. Here we have a simple item in a table which stores access records to a data center. We want to revoke this access to users after 30 minutes. And rather than creating an application to count down minutes and deleting access from the entire table, we can set TTL attribute expire and set the value of 30 minutes from the current time in epoch format, which will essentially delete the item from the table. The attribute name, in this case expire, can be set to anything else. However, when enabling TTL on a particular table, make sure to specify the correct attribute name which you'll be using for this purpose as the TTL parameter. Another thing to bear in mind is that when TTL attribute is set, it is not required to include them to every item. Items without TTL attribute will never be deleted. We'll now create a simple table, enable the TTL option for expire attribute, add items with TTL attribute and observe deletion. Now that we are logged into the console, let's create our table. Again, it doesn't matter which region we create our table in this case, so we can stay in Ohio for now. Let's create a table and call it TTL table. We can name our partition key name again. In this case, we won't use any sort keys. We'll also use all default settings here. Let's create this table. We'll wait now until our table provisions. In the Overview tab, there is an option for Time to Live attribute. It's disabled for now, so let's click on Manage TTL. Here we can choose any attribute name, so let's call it expire as in our example. There are a few more options such as DynamoDB streams. This serves as a backup in case TTL is configured badly and DynamoDB removes items which are not supposed to be deleted. Let's click Continue. As you can see that the time to live attribute has been set to expire. Let's input an item with expire attribute and one without it. Go to Items and select Create Item, and switch the editor to text mode again. Let's store the item that does have expire attribute now. This item is set to expire in 10 minutes from my current time, so we'll speed this up. Let's store the one that does not have expire attribute now. And now, after 10 minutes, the item is deleted from our table. In previous clips in this module, we talked about provisioning capacity. But what about capacity of particular partitions where the items are stored? Surely SSD drives do not have unlimited operations per second, and that's correct. They don't have unlimited capacity in the world of DynamoDB either. As we talked about in previous module about the way DynamoDB stores data based on primary key. Now let's talk about problems that can arise when primary key is designed the wrong way. Let's take an item where name is the partition key and age is the sort key. The application which accesses the table in this case is a public website of a large company, Globomantics, which displays employees, their good deeds, and the best employees of the month. For instance, Lucy stores 4 items within the employee table: Bob, who is 23, Bob, who is 26, 55, and 30. Due to the partition key being Bob in all 4 cases, the items are stored on the same partition. Now Bob, who's 23, becomes the employee of the year, which gets global media attention and therefore a huge amount of traffic. What happens next is that the partition where all 4 items are stored becomes overloaded with traffic. This is otherwise called a hot partition. This also means that any additional queries for those items are significantly slowed down. For instance, anyone wanting to view Bob, who's 26, will feel degraded performance of the public website. So what can be done in order to prevent this issue? Because we already know employee name and employee age, what we can do is to combine partition key and sort key and join them with a dash to create the new partition key, therefore effectively removing sort key age out of primary key. Let's describe the scenario with the revised primary key. Lucy again stores items with the revised primary key. All of these items will now be stored on the different partitions, eliminating performance degradation of one partition. Some of the recommendations for partition key include using combinations of known information. This is so that we are able to query based on partition key. For example, we cannot query items with a revised partition key if we don't know the name or age itself. Also, querying is difficult with the randomly generated partition keys. This includes incremented integers or randomly generated strings, as we will not have any way of querying items in our table. A type of random string that could potentially identify an item would be if the string is stored within an application. For example, users themselves can query the table with their randomly generated user IDs to fetch their profile preferences. As for sort keys, making sure that data can be queried with starts with, between, more than, and less than is beneficial to retrieve commonly needed groups of related items. The following example will let you make sort queries at any level of residency for Bob. We can look for Bob, but we are not sure what city he was from, but we know his continent and state. We can now make a starts with query, leaving the city out. The query will return all Bobs within the same continent and state. But we'll talk more about data querying in the following module. In this clip, we need to create an elaborate DynamoDB table based on the instructions from the developers. The table will serve as an employee directory for a very busy website. So primary key has to be designed well in order to avoid storage limitations as well as throughput capacity limitations. The developers have also said that the website can store random strings within the code to access objects within the table. The same table will also be used by an application that will update and track access to workplace building. Now this application will also be able to store random strings within itself, so we could definitely use that to access data somehow. The application should update employee item with the day accessed in epoch time. The application should be able to sort returned items based on employee name, but query based on date. For example, get items where date is 6th of May and name contains Bob. The developer specified the third application that will access the table. This application will track down temporary employees and contract workers in various departments, so we'll need to query full items based on employee position and contract type. The requirement for this table is that it needs to be accessed from Sydney, Dublin, Oregon, and India with minimal latency. Another requirement for this table is to remove temporary employees automatically at the end of their contract. The developers also said that the website will be extremely unpredictable when it comes to traffic, so we need to keep that in mind. So we are logged into the console. Let's think about the requirements before we can start creating this table. The developers have specified that the application can use random strings to access data. So in this case, we can use a unique ID number that will belong to each employee. This number can be generated when a new employee is hired. This will be also a great way to split traffic across multiple partitions to avoid any bottlenecks. We won't need any sort keys nor any local secondary index, since the items will be uniquely identified by the employee ID. The developers said that the website using base table capacity is extremely unpredictable and have not specified any additional details. Therefore, on-demand auto-scaling would be the best option in this case. Now, however, we need to make sure that we are creating the initial table in one of the regions closest to the desired locations: Sydney, Dublin, Oregon, or India. So we need to switch regions now. I'll go to Ireland in this case. So let's call this table Elaborate Employee Table with primary key consisting of only partition key called ID, and check Use Default Settings and switch Auto-Scaling to On Demand. Now create the table and wait until it provisions. Now what we can do is to deploy Global Table into remaining regions. Go to Global Tables tab and enable Streams. This table needs to be accessed from Sydney, Dublin, Oregon, and India. We already have the table provisioned in Ireland, so Dublin is done. We can create a replica table in Sydney region first. Click on Add Region and choose Sydney. Now let's add Oregon region. Click on Add Region and choose Oregon. Now let's add India. Unfortunately, AWS does not have global table service in Mumbai region, which is closest to India, but we can choose a region that's closest to India to minimize latency. In this case, region closest to India is Singapore. Let's click on Add Region and select Singapore. Now we have to create global secondary indices. Before we start, however, let's recap what the requirements are real quick. The application that will track access to the workplace building will write to our table using our ID partition key, so we don't have to worry about that. However, the application needs to access items based on time in epoch format or any other format. It also needs to sort items based on employee name. What we can do is to create a global secondary index with its primary key consisting of partition key called last access set to integer type and name attribute set as the sort key. So let's create it. Click on Indices tab and then create index. Let's set the partition key to last access and change the data type to integer. Add sort key and name it name. Let's name this index Access Application Index. Let's switch the projected attribute setting to keys only. This is due to the fact that the application will query items based on last access and name and probably won't need any other attributes. Click Create Index and wait until it provisions. The second application requires to query this table to see position and contract type of every worker. So let's create an index where position is the primary key and contract type is the sort key. That way the application will be able to query necessary data. So let's create this index. Click again on Create Index. We'll name the primary key module. To summarize, in this module we went through calculating throughput capacity, which we found was essential to correct provisioning of DynamoDB tables. We learned about read consistency and how to calculate necessary throughput using both eventual and strong consistency. This is also where we learned that strongly consistent reads are much more expensive than eventually consistent reads, but a lot more reliable in terms of retrieving up-to-date data. We learned that DynamoDB can auto-scale two different ways, with provisioning capacity, where we set a static range, which DynamoDB can then use to scale up and down, and on-demand auto-scaling with an unlimited range. We also learned about advantages and disadvantages of each. We learned about the local and global secondary indices and how we can use them to access data within our table. We went through DynamoDB global tables, where we learned about creating multiple tables in various regions that can be in sync with each other for minimal latency. We also learned about time to live attribute and how we can use it to remove unwanted items from our table. We learned how to design partition and sort keys for maximum efficiency while avoiding DynamoDB limits. And at the end we created an elaborate global table where we designed the required primary key for the base table, deployed table globally to all required locations around the world, designed and created global secondary indices for better data access, and applied additional time to live feature which will remove unwanted temporary employees from our table.